Hey everybody, Mr. Judson here. Hope you all had a good weekend. So let's see, I've started to put together a schedule, and I'm not going to slide it out here so you can see it yet just because it's sort of a rough draft, but I wanted to at least let you know a few things. One, just in looking ahead, there's a lot of things, little tiny pieces of information that aren't really huge ideas in the area of trig. So we have a lot of things coming up that we can skip, and so my main focus is going to be on what's really important moving forward to calculus, and what's important in terms of taking the Central Washington final. So I have a schedule that I think is pretty well set, and I have our Central Washington final scheduled for June 14th. Remember, our last day of school is June 19th. It's a Friday. We've had 3 days added to the year, but we're going to be able to take our final exam on June 14th, and I'm not really going to have anything from that point on. So that's the target date. If for some reason we just need an extra day, well, we've got that available, but that's what I'm shooting for. And so we've got really just two things to do in Chapter 5. We've got something called the double angle identities, and there's also something called the half angle identities. We'll do those tomorrow, but we're going to look at double angle for today. Also, one more piece of information. So this coming weekend is Memorial Day weekend, and normally I use Mondays to do my videos and get things started. Today's actually Monday that I'm working on the video, but it's your guys' lesson for Tuesday. Since next Monday is Memorial Day, I'm not going to have anything for you guys on Tuesday, so next week will just be a Wednesday, Thursday lesson. Okay? All right, so Central Washington final on June 14th. Next week we just have Wednesday and Thursday to look at. All right, so let me just slide the book underneath here, and we'll take a look at the double angle identities. I'm going to go ahead and zoom in. All right, so here's the identities that we want to look at. When we say double angle, we mean that this angle is twice as much as whatever, whether it's 2x, 2 theta, or twice as much as something that we already know. I don't know. But we're just doubling the angle. And so we're going to go ahead and look and see, where did each of these come from. These are a little bit easier to prove and understand since we have our sum and difference formulas. Okay? Sum and difference formulas, that's these ones right here. That's what we learned last week. Sum and difference for sine and cosine, and then also for the tangent. All right, so let's start with the first one. Sine of 2 theta. So really that's just the sine of theta plus theta, right? Theta plus theta would equal 2 theta. And so when I look at this, I can now think of the sum and difference formulas. And what they said is you take the sine of the first angle, cosine of the second angle, which happens to be the same, plus, and then switch the angles. So now I have sine of the second angle, cosine of the first. Well, in the end, you look at that and they're both the same, so when you add that, you just get 2 sine theta, cosine theta. And so there's our double angle formula for the sine function. All right, let's try cosine. So cosine of 2 theta, I'll approach this the same way. That's cosine of theta plus theta. And so if I use the sum and difference formula from last week, it said take the cosine of the first angle times the cosine of the second angle, and then what I put here should be opposite of this, so minus, and then the sine of each of those angles. Well, since those angles are the same, I get cosine squared of theta minus sine squared of theta. And so there's one of our double angle formulas for the cosine. Now, there's actually 3 different formulas for this. And the reason is we can change either one of these using one of those Pythagorean identities. So if I think sine squared plus cosine squared equals 1, and let's say I want to change this cosine over to sines, I would say that a cosine squared equals, when I move that over, it becomes 1 minus the sine squared. So if I put that in right here, 1 minus sine squared theta minus this sine squared theta, then what I get is 1 minus 2 sine squared theta. So that would be a second option for the double angle for the cosine. Now, what if I would have changed the sine instead of the cosine? You know, I solve this and I say that a sine squared is equal to 1 minus a cosine squared. And I'm going to put that in place of this. So I could have also had a cosine squared theta minus, and then what I'll substitute in for a sine is 1 minus a cosine squared. And then when I distribute this negative sign, I would get cosine squared theta minus 1 plus a cosine squared theta. And so what I get is 2 cosine squared theta minus 1. And there's a third option for the double angle formula for a cosine of 2 theta. So usually the most common question I get asked here is, well, which one of the 3 should we use? And it really depends on the rest of the problem. I suppose I could even say it doesn't really matter, pick one. But let's say I look at a problem and maybe somewhere else in the problem I see a positive sine squared theta. Well, I'd want to choose this first one because then that negative sine squared plus the sine squared theta, those two would cancel out and equal 0. And I got rid of something. Or maybe everything else in the problem is in terms of the sine function, and so then I would choose this one. Or maybe everything's in terms of the cosine and I choose this one. So it's, you know, we just kind of have to look at the problem and decide which one of those is the best to choose. But we do have those 3 options available. So let me just kind of back up and summarize this. When we have a sine of 2 theta, we can choose cosine squared theta minus sine squared theta, or we can choose 2 cosine squared theta minus 1, or we can choose 1 minus 2 sine squared theta. All 3 of those work. All right, and then the last one is the tangent of 2 theta. We want to see what that's equal to. So I'd write that as tangent of theta plus theta. And again, use our sum and difference formula. So our sum and difference formula said you take the tangent of the first angle plus the tangent of the second angle over 1, and then I want the opposite of that, so minus, and then tangent of the first angle times tangent of the second angle, which again, first and second are the same. And so then what that gives me is 2 tangent theta over 1 minus tangent squared theta. And there's our double angle formula for the tangent. There is no double angle for a secant because, you know, if I was going to do the secant of 2 theta, I'll just do this and at the end I'll flip that answer over. Or, you know, a secant of 2 theta, I'll do any one of these 3 and when I get done, flip it over. Cotangent, same thing. Just take this fraction, flip it over, and that's our cotangent of 2 theta. All right, let's do a practice problem. All right, so here's our double angle identities, if you need to look at that. So here we're saying if the tangent of theta is equal to 3/5, find the cosine of 2 theta. You guys go ahead and try it. All right, so we've kind of done some problems like this before. It was always if the tangent equals 3/5, find the cosine of theta or the sine of theta. Well, now they're changing it, but I still start that problem the same way. I start out by drawing a triangle. I'm not told which quadrant we're in, so whenever they don't tell me that, I just assume the easiest, first quadrant. Reference angle has to touch the x-axis, right? It never goes up here. And we know tangent from SOHCAHTOA, opposite over adjacent. So 3/5. This is not a 3, 4, 5 triangle, right? If we put a 4 here, then we're saying that the hypotenuse is shorter than one of the legs. That can't happen. So I need to do a Pythagorean theorem here. So I want to do the square root of this squared plus that squared. So 25 plus 9, that's 34. And that does not simplify. So there's our hypotenuse. So we know that the cosine of theta can be 3 different things. I'm just going to choose this second one. I'm going to choose 2 cosine squared theta minus 1, which means I've got 2, and the cosine is adjacent over hypotenuse. So 5 over the square root of 34, and I have to square that and then subtract 1. So if I square this, I would get 25 root 34 times root 34 is 34 times 2 minus 1. So that would be 50/34 minus, I'm subtracting 1, so I'll just call that 34 over 34. And so 50 minus 34, that would be 16/34. And I'm still amazed. I'm thinking back to our last test we took. How many people don't think about reducing fractions? That will never go away, you guys. You always have to reduce. You should always think of that. So if I divide by 2, I get 8 over 17. And that's as far as that can go. There's my answer. All right, let's try another one. So I'll start off with the same thing here. If the tangent of theta equals 3/5, find the sine of 2 theta and the tangent of 2 theta. So I probably should have left this picture in here, but I'll just go ahead and draw it real quick. Tangent is opposite over adjacent, and this was the square root of 34. Okay, so you go ahead and find these two. All right, so I know that the sine of 2 theta is equal to 2 sine theta cosine theta. It's this identity right up here. And so that means I've got 2 times sine of theta is opposite over hypotenuse, so that would be 3 over root 34. And cosine theta is adjacent over hypotenuse. So I got 2 times 3, that's 6, times 5, that's 30. This is over 1, so I get 1 times root 34 times root 34, that's 34. And if I reduce this, I get 15/17. There's my first answer. So these aren't really that hard. We just had to understand the identity and then be able to use it. So for tangent of 2 theta, I get 2 times the tangent of theta over 1 minus tangent squared theta. Well, I don't really even need the picture to do this. I've got tangent of theta right here. So this is 2 times 3/5 over 1 minus 3/5 squared. And so what I get is 6/5 over 1 minus 9/25. And again, you can go ahead and subtract these first, get a fraction divided by a fraction, flip this over and multiply. If you feel comfortable with that, go right ahead and do that. I like this idea of, find the least common denominator and multiply everything by it. This is a complex fraction. So my least common denominator is going to be 25. So I'll multiply this by 25, this by 25, and this by 25. Each term. I got 1, 2, 3 terms. And so now, here if I do 25 divided by 5, that's 5, times 6, that's 30, over 25 minus, those cancel and I get 9. And so what I get is 30 over 25 minus 9, that's 16. Divide by 2, you get 15 over 8. There's our answer. All right, let's try another one. All right, so we're going to try and solve this equation. I only want answers from 0 to 2 pi, which means we're only going around the unit circle once. And, the first thing you notice here is that, okay, I got x's and I got double angles. When you solve an equation, all angles have to be the same. They have to match. You cannot solve an equation where you've got double angles and regular angles. Okay, so we have to make a change here. And I've always said, get rid of messy angles. Anything other than x or theta is considered a messy angle. So I'll use my double angle formula and I'll change this into this right here, 2 sine x plus sine x. So 2 sine x cosine x times a sine of x equals a cosine of x. And I'll kind of stop there and let you guys take it from there. Okay? All right, so I would rewrite this as 2 sine squared of x times a cosine of x equals a cosine of x. And I always want to be real careful of something here, because a lot of people could look at this and go, well, let's just divide both sides by a cosine of x, and that way we get rid of it, and we only have one trig function. Problem with that is every single time you do that, you eliminate a potential answer. Okay? So we want to avoid dividing by a trig function as a way of getting rid of things. I don't want to do that. Okay? I do know I need to set the whole thing equal to 0. So I'm going to have 2 sine squared of x cosine of x. I'll bring this over and subtract it. Don't look at this and go, well, that minus that is 0, so I can get rid of it, because order of operations says you have to do multiplication first. You can't just subtract away part of this. All right? So I could, using a Pythagorean identity, change everything to cosines. We could do that with this one. It would work. It would be fine. I could also factor out a cosine for each of these terms. And we've said that when solving an equation, you have to have one trig function, or each factor has to have one trig function. So if I factor a cosine of x out, now what I have is a situation where this factor has one trig function and this factor only has one trig function. And remember, in order to multiply this times this and get 0, either that equals 0 or all of this has to equal 0. So cosine x has to equal 0, or 2 sine squared of x minus 1 has to equal 0. See, now what I have is two separate equations where there's only one trig function in each of those. All right, so where does the cosine equal 0? Cosine of x equals 0 here and here. So that means x would equal pi over 2 and 3 pi over 2. Here, if I move the 1 over, it becomes positive, and then I'll divide by 2, so I get sine square root of x equals 1/2. And then I got to take the square root. And so the sine of x will equal plus or minus. We're solving by taking the square root of both sides. Square root of 1/2, which equals plus or minus, square root of 1 is 1. Square root of 2, I don't know what that is. So I got 1 over root 2. And if I simplify that, I get plus or minus root 2 over 2. And we know that the sine equals root 2 over 2, either positive or negative, at these middle tick marks. So those would be my remaining answers. So here x equals pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. There's my answers for this equation. Now, I really should double check each of these. I don't know if you guys remember this, but when we were solving equations, we had this idea of extraneous roots. I've made some changes to the equation. Is it possible I introduced a new answer? Maybe. So if I plug pi over 2 into here, the 2's would cancel. I'd get sine of pi, which is this right here. My y-coordinate is 0, so 0 times anything, it's going to be 0. And the cosine of pi over 2, that's 0. So this one works. If I use 3 pi over 2, again, 2's would cancel, so I get sine of 3 pi. So here's 1 pi, 2 pi, 3 pi. So the sine would be 0 again. Cosine at 3 pi is 0. 0 times anything here is 0, and 0 does equal 0. So yes, both of those checked out. And then I'd have to plug each of these in. It's kind of a lot of work to check this out. Here's another way you can do this. If you were to graph, so I'm going to graph the original problem, but I'm going to move this cosine over to the other side. So I'm going to graph sine of 2x times sine of x minus a cosine of x. So sine 2x times sine of x minus a cosine of x. And I'm going to graph it from 0 to 2 pi. So let's see, make sure I'm in radians. And for my window, I'm going to go 0 to 2 pi. My y values, if I just go like -3 to +3, that's fine. And I suppose on my x-axis I can put tick marks every pi divided by 2. That's what we normally do when we graph, right? As I go from 0 to 2 pi, I should see this equation I'm graphing cross the x-axis 1, 2, 3, 4, 5, 6 times. It should cross at each of the solutions. And so I just crossed it pi over 2. There I just hit 3 pi over 2. So I don't know how well you guys can see this. Let me zoom in. So if I look at this, I can see that I'm crossing at 1, 2, 3, 4, 5, 6 places. This right here is pi over 2. This right here is 3 pi over 2. Alright, let's try this one. So we said there's no double angle for the cosecant and cotangent, but again, it doesn't mean we can't do that. I know that the cosecant is the reciprocal of the sine, so using this picture, I'm going to find the sine of 2 theta, and whatever that answer is, I'll just flip it over. Okay, same thing here, I'll find the tangent of 2 theta, and whatever that is, I'll just flip it over. Alright, you guys go ahead and try this. Alright, so the sine of 2 theta is going to equal 2 sine theta cosine theta. And to find each of those, I'm going to have to do the Pythagorean Theorem to figure out the length of the hypotenuse. So this will be the square root of 64 plus 9, which is the square root of 73. And that does not simplify. So I get 2 times the sine, which is opposite over hypotenuse. That's 8 over root 73. Times the cosine, which is adjacent over hypotenuse. That's 3 over root 73. And so what I get is 6 times 8, that's 48 over 73. I don't believe that simplifies. But I'm not looking for the sine of 2 theta, I'm looking for the cosecant. So I just got to remember to flip this over and say 73 over 48. Make sure you don't do this. I've seen this a lot in the past. People go, okay, I got to flip it over, so that's equal to 73 over 48. Are those two fractions really equal to each other? I don't think so. I don't think so. So yeah, we don't want to say that. The sine is equal to this, the sine of 2 theta is equal to that. We can't just keep on going with equal signs. We've got to start over and say now the cosecant of 2 theta is equal to the reciprocal. All right, so there's that. Cotangent of 2 theta. So I'm just going to do this. I'm going to say cotangent of 2 theta. And I'm going to flip this over right from the start. 1 minus tangent squared theta over 2 tangent theta. So the tangent is equal to opposite over adjacent, 8/3. So I've got 1 minus 8/3 squared over 2 times 8/3. And so that's going to be 1 minus 64/9 over 16/3. And if I want to get rid of that complex fraction, I just want to multiply everything by the least common denominator, which is 9. So times 9, times 9, times 9. And that equals 9 minus, those cancel, 64. Here, divide by 3, I get 3. So 16 times 3, that's 48. And so 9 minus 64, that's going to be a negative 55 over 48. And I don't have to flip it over because I already did that up here. So that's it. We're done with that one. All right, that's it. That's what we have for today. C15. It's on page 415. And we're going to do 1 to 27 odd. I'm really trying hard to do mostly odds because, you know, that way you guys have access to the answers in the back of the book, and you also have access to answers through Calc Chat. Remember, calcchat.com. If you ever need help, you can go there and see the work that they do. It's got steps. It's a good resource. If you're not using this, you should be. Yeah. All right. So just kind of a reminder of a couple things. Our Central Washington final is going to be June 14th. We only have 2 days next week because of Memorial Day weekend, and I won't be here. I'm going to be gone, and so I can't make videos and get them prepared on Monday. So next week, Wednesday and Thursday. All right, that's it, you guys. Take care. Stay safe. I'll see you tomorrow.